Hello everyone. So in this short video we will introduce the Z transform, which is in module number 5, and it is valid only for discrete time systems. Okay, let us obtain the Z transform of an arbitrary signal. Before that, let us understand about complex exponential signals. Whenever we write any signal in the form Z power n, suppose if we call that sequence as x of n, this is a representation for a complex exponential signal with Z being considered as R into e power j omega. R represents the damping factor, and if we substitute here, we get in this form R power n into e power j omega n. If we write it in rectangular form, R represents the damping factor, and the real part from this complex exponential will get the cosine term and one more sinusoidal term in the imaginary part. Hence, in general, this function z power n is a complex exponential signal. What will happen to a discrete time system whenever we feed this kind of input at its this kind of signal at its input? So let us consider the block diagram representation of a discrete time linear and time invariant system, which has impulse response as h of n. To this we feed input as x of n, which is given as z power n, which is a complex exponential signal, and let us try to calculate y of n, and by working out simple convolution sum. Okay. So this is a discrete time system. Y of n, which is the output, is given by convolution sum, which is h of n convolved with x of n. Okay. So using the convolution sum operator, we can represent this as sum of products, which is k from minus infinity to plus infinity. K represents summation variable. H of k, x of n minus k. This we already seen in class, but we know what is x here. Substitute n in x of n as n minus k and rewrite this in terms of z. So just let me write it here. Y of n now can be quickly simplified in this form: k from minus infinity to plus infinity, h of k into z to the power of n minus k. Here everything except the term z power n is a constant, we can bring it outside. This is z power n, and we have summation k from minus infinity to plus infinity, h of k, z power minus k. Now we represent this term as transfer function of a digital system, denoted as h of z. So z power n into h of z. Hence we show that for a discrete time LTI system, whenever we feed a complex exponential across its input, we get the same complex exponential across its output, which is scaled by an amplitude and a phase term. That is nothing but your transfer function. This is popularly represented as transfer function of a digital system. Okay, transfer function. Hence, this is also known as eigenvalue, eigenfunction property of a discrete system, where the output is same as the input applied, only the input, when it is scaled by h of z, we get y of n, discrete output. So generalizing now the representations, if we are knowing the impulse response of a discrete system in the time domain, its transfer function in the digital domain is represented as h of z. It is a reversible process, and this is representing a general Z transform expression notation. For an arbitrary sequence, for arbitrary discrete time sequence x of n, its Z transform is denoted as capital X of z, where this x of z can be represented using this summation form. Okay, that's all about developing the Z transform for a discrete time system, from which we get an important idea known as transfer function. And if we substitute z here as, or if we evaluate the transfer function on unit circle by substituting r as 1, then we obtain frequency response of a digital system, also known as h of e power j omega. Okay, that is popularly obtained by DTFT expression. Okay, thank you. Stop. Okay, we have seen that the output due to a complex exponential input is the same complex exponential input multiplied with this scaling factor h of z. This is known as transfer function. From here we see that knowing h of n, we can get its frequency response that is dependent on independent variable z. Generalizing this to arbitrary discrete time signal x of n, we get its transform represented as h of x of z. That means in general, the z transform of a discrete sequence is represented as capital X of z, which is equal to summation n from minus infinity to plus infinity. Just I have used the independent summation variable instead of k as n. X of n into z power minus n. This is the standard expression for z transform of an arbitrary discrete time signal. Using this starting equation, we will try to find out the region of convergence where exactly the z transform is valid, because we know that z equal to r into e power j omega. Okay, that also let me note it here, where z is r into e power j omega. Z transform evaluated on unit circle, that is for z equal to e power j omega, results in discrete time Fourier transform, which is DTFT, which is a continuous function of frequency variable omega. This is also another important relationship. Okay, we have developed a relationship between discrete time Fourier transform and Z transform. Very important point is, for the existence of discrete time Fourier transform, your sequence that you take must be absolutely summable. That means I take the absolute values of the sequence x of n and add the sample values all the way from minus infinity to plus infinity, and if I have the sum as finite, then DTFT was existing. Because if you see the standard DTFT for standard signals such as a power n u of n, DTFT is 1 by 1 minus a into e power minus j omega. A into e power minus j omega. Sorry, this is the representation for omega. And here this angular frequency is represented with uppercase omega. Sorry. Very important condition here is that the magnitude of A should be less than 1. If it is less than 1, then our sequence will be absolutely summable and we have DTFT existing for only this specific case. In Z transform, we don't have to give any condition for a sequence. Irrespective of whether the sequence is absolutely summable or not, Z transform exists. Hence, Z transform is a generalized representation for any arbitrary discrete time signal. And the special case for Z transform for a specific value of omega or specific value of Z evaluated on a unit circle results in DTFT. Means if we evaluate Z DTFT at unit circle by substituting Z as e power j omega, then we get the Z transform. That means a power n u of n. When we calculate it, we will going to be deriving this. Z transform for this will be 1 by 1 minus a Z inverse. because I have considered Z as e power j omega evaluated on a unit circle. There is no restriction on the value of a. Sequence can have a value greater than 1. If a is greater than 1, we know that it is going to be an exponentially growing discrete time signal. So this is growing discrete time exponential signal. And when a is smaller than 1, it is decaying exponential signal. Decaying exponential signals are absolutely summable. Similar to Laplace transform, special case of Laplace transform evaluated on an imaginary axis results in continuous time Fourier transform. Same way, for digital system, Z transform is a generalized representation. Okay, so let me continue with this representation of discrete sequences. I will just use a value greater than 1, a value lesser than 1, and we have u of n, that is a right-sided infinite duration sequence with a step value of 1. Okay, so if I want to sketch half power n u of n and compare this representation to 2 power n u of n, we know that u of n is a right-sided sequence. The sample values from index 0 up to infinity, they will be in decaying form. At index 0, sample value is 1. At index 1, it is half. At 2, it is 1 by 4. At 3, it is 1 by 8. For negative time indices, the sample values are 0. What I was explaining all this time is discrete time Fourier transform, that is this one. This is DTFT. Discrete time Fourier transform exists to sequences which are absolutely summable. Okay, this is absolute summability. This is one of the requirements for Dirichlet conditions. The general magnitude of this sequence is half power n. Where only if the sequence is absolutely summable, then DTFT exists. Whereas for Z transform exists even for sequences which are not absolutely summable. That means if you add up this, means the sample value at index 1 is 0 is 1, plus next is half, 1 by 4, this goes on up to infinity. It is a geometric series. The sum of this geometric series will be first term divided by 1 minus common difference, which is half. 1 minus common difference, which is half, which is definitely lesser than infinity. If you take another example, another sketch of plotting 2 power n u of n. This is a discrete time growing exponential signal. That means at index 0, the sample value is 1. At index 1, it is 2. At index 2, it is 4. At index 3, it is 8. And if we keep plotting it, the sample value will keep on growing. This sequence is not absolutely summable, because if we add it, the sum of the sample values of the sequence x of n from 0 to infinity, n from 0 to infinity will be equal to infinity. Hence, just want to conclude that Z transform do exist for these kind of sequences. Maybe it is a right-sided infinite duration signal, or left-sided infinite duration signal which is anti-causal, or both side double-sided infinite duration signal. How to check the validity or the region where the Z transform is proper, or how to where the Z transform is valid? The region where Z transform is valid is denoted by the range of values of Z. That is referred to as region of convergence, ROC. ROC is a region where Z transform is valid. Okay, that is a connected region, and in this connected region, our Z transform, which we calculate, the magnitude of Z transform is finite. We will see about ROC in the next video.